Hello again, this is the section 2.6 in the book, and we're going to talk about adding Cartesian vectors. So if you look at the figure on the right, we have two vectors, A and B, and we want to find the resultant R. So we can write, just to find those vectors, A, magnitude of the x component times I direction, magnitude of the y component times the j direction, z component magnitude times k direction, and likewise for b. And we want to find the resultant R, which is the sum of A and B. This is the exact same process as for vectors in 2D. And you see in the picture there, we have A and B, and then the resultant R, its components define the edges of that parallelepiped, I think it's called. Anyway, a 3D rectangle. So you see that the x component of R is just the sum of the x components of A and B. So AX plus BX in the I direction. So AX plus BX is the magnitude of the x component of R, and it's in the I direction. And then the same thing is true for the y direction and the z direction. So that's how we add vectors in 3D. Now it might be the case that we have more than two vectors, and if so, we just repeat this. So if we had C, then Cx would be included in here, Cy and Cz. So if we have a lot of forces, which we will, and they all act at a single point, so they're concurrent, and we want to add them up and find the resultant, or the effective force of all those, then that is given by, so this resultant force is the vector sum of all the forces. Again, this is vector addition, it's not scalar addition. So you can't just add the magnitudes through vector addition. That's equal to, so here you can do scalar addition. You add the scalar, the magnitudes in the x direction of all the forces, multiply it by the I direction vector. You add the magnitudes in the y direction of all the forces, so summing all the y components, multiply it by the j direction vector, and then sum the magnitudes of all the z components, multiply it by the k direction vector. So that's how you add multiple forces in 3D. And we'll do a couple of example problems on this topic. I'll leave that equation at the bottom because we will use it again. So if you look at the next figure, this is example 9 in chapter 2. And the question is, what's the resultant of those two forces that are acting on that I ring, I bolt? So they're already decomposed into their Cartesian coordinates. We see F1 is 60 in the y direction and 80 in the z direction. So it's in the YZ plane, F1 is. F2 is not, it's in one of the octants. So, but we have its I, j, and k components. So we'll just use this equation. The resultant force vector is equal to sum of the x components times the I direction, sum of the y components times the j, sum of the z components times the k. So I'll write it out. F1x plus F2x I f1x plus f2x times I, f1y plus f2y times j, f1z plus f2z times k. And numerically that ends up being f1x is 0, so 0 plus 50. And then in the y we have 60 minus 100. And then the z, 80 plus 100. So the final answer is 50i minus 40j plus 180k. And I guess that looks something like, so we've got x, y, and the right-hand rule, z. We've got 50 this way, minus 40 that way, and 180 this way. So here's fr prime, and add to it that, so here's fr. Got frx, fry, frz, and there's fr, which is the sum of those. Now the next problem that we'll do, we have, again, just two forces, and they're concurrent. And we want to find the resultant. In this case, though, we're not given the Cartesian components of the two forces. So it's the same problem, but we're adding the step of we have to decompose the forces into their Cartesian components. And then once we have those, then we will simply use this equation and get the resultant. So we'll call, okay, F1, we know the magnitude. And from the figure, you're supposed to see that it's in the xz plane. See the parallelogram that is made up of its components? That is in the xz plane. So you only need one angle. I guess the other angle could be that theta is 0. So F1 is in the xz plane and F2 is in some octant. So F1. The easiest way to keep track of this, I think, is to just write it out in vector format, and that way you can keep the direction and the magnitude of the components straight. Like if you just write the magnitude, like f1x, and then write its own equation, when it comes time to formulating the vector, you might miss the sign. So I like to keep everything in vector format. So F1 is, the x component is 300 times cosine of 30. Oops, that's a bad 3. 300 cosine 30, and that's in the I direction. It has no y component, and the z component is pointing down, so that we'll just say minus 300 sine 30 k direction. And yeah, I didn't calculate the numbers beforehand, and I don't think I want to bother getting out a calculator now, so we'll just leave it in this format. We won't get a numerical answer. So F2, the vector F2 is, so the x component, we have, the x component is the magnitude F2 prime. So that'll be the component of F2 that's in the xy plane, and then times sine of 30. Plus F2 prime, the magnitude, times cosine of 30. And here we have sine for the x because you see where that 30 degrees is defined relative to the y. So just looking at that triangle, we see that the x component is opposite the angle 30 degrees. So I'll draw that triangle again. Here's 30. There's F2 prime, and this is x, and this is y. So the x component of F2 prime, the x direction, is opposite the 30 degrees. So that's why we use sine of 30 for the x component. And then the y component, f2 prime y, this side here, is adjacent to the 30 degrees. So that's why we use cosine of 30. So we've got f2 prime for the hypotenuse, f2 prime x, f2 prime y. Well, that's really f2 prime x is the same as f2x. No, that's not true. Yes, that is true. Okay. f2, and then f2z is just the magnitude f2 times the sine of 45. But again, that's pointing down in the z direction, so we'll go ahead and put a minus sign there. f2 sine 45 times the k direction. Okay. And then expanding the value for f2 prime, because we don't know what that is yet. So f2 prime is equal to the magnitude f times cosine 45 degrees. So this f cosine of 45 is the magnitude f2 prime. And so then we're just substituting that into this equation. So now we have, here's the x component of f2 cosine 45 sine 30. So this right here gives you f2 prime, and then this right here gives you the x component, like from that equation. And again, just substituting for f2 prime here. f2 cosine 45. It's the same value in the x and y components, f2 prime and f2 prime. f2 cosine 45, f2 cosine 45. And then to get the y component of f2 prime, we multiply by cosine of 30. So now we have the Cartesian components of f1 and f2. And to get the resultant, we just add the x and y components. So this is going to be pretty long. I'll go ahead and scoot over to make sure there's room on the board. Oh, well, we know the magnitude of f2. It's 500. So now I'll substitute in f500 for f2. And then the y component for f1 is 0, so it's just f2 times cosine 45 cosine 30. So the y component of the resultant is just the y component of f2. And then summing the z components. Just being sure to keep the signs straight. So we have I put the minus sign out here since they're both negative. And so 300 sine 30 plus 500 sine 45, and then they're both multiplied. That sum is multiplied by is negative. So minus this sum. So there's the answer. This line gives you the answer to the question. That's the result for us. And that concludes the section on summing Cartesian forces, which is 2.6 in the book.